after the three-dimensional A type packing, now we are having a three-dimensional AB or ABC type of packing. As the name says that AB or ABC, from that we can say that, from this naming only we can say that AB, that means where the alternate layers are same, that is after the one layer the next layer will be of some different type, then next of different type, then next of different, right? ABC means here we have three different types of layer, A, B, C, and after C again A will come. In three-dimensional packing, A and B stand for that capital A and capital B. They represent the layers, the arrangement of a particle in layers. We have learned about the two layers, that is AAA type layer, that is a square closed pack layer, and the second is hexagonal closed pack layer. Now, from the square, when the square closed pack layer were placed one above each other, we come to know that we are getting a three-dimensional AAA type packing, whose coordination number is 6 and also known as a simple cubic packing. Now, after square closed pack layer, now let us consider the two-dimensional hexagonal closed pack layer. So in animation you can see that here we are having a hexagonal closed pack layer. Hexagonal closed pack layer is known as two-dimensional AB type packing. Here the word two-dimensional, three-dimensional simultaneously have to think about the layers. If I am saying two-dimensional AB type packing, that means I am just talking about a single layer where the arrangement of particle in a rows represent the where A and B stand for the arrangement of particle in a row. So here we are having a two-dimensional hexagonal closed pack layer. Now in this two-dimensional hexagonal closed pack layer, you can see that here we have trigonal voids. The voids, that is a space which is left between the particles. So in this you can see that here we have the trigonal voids. Here I'm dividing all the voids. Trigonal void means which is triangular in shape. I'm dividing it into two categories. The some voids are pointing upward side, while the some of them are pointing downward side. I'm giving a name to them. All the voids which are pointing upward side, I'm calling it as a void A, and all the voids which are pointing downward side, I'm calling it as a void B. So ultimately here we have two types of void, that is void A and void B. Now this is only a single layer, the single layer with the two different types of void, that is a void A and void B. Now let's talk about the now here we are talking about the three-dimensional packing. Three-dimensional packing means now I'm going to keep the another layer on the first one. So now it's a time to keep the second layer on the first layer, because once I keep the layers on the layer, I will get height also and it will become three-dimensional. So now when I'm keeping the second layer on the second layer, now there is a two possibility. Means in this case now I'm going to keep the second layer, the spheres of the second layer on the voids of the first layer. So we have two possibility. Either I will keep the spheres on void A, or I will keep the spheres on void B. Keeping the spheres of the second layer of the second layer on both void A and void B is not possible. Either the balls will be kept on the A void or it will be kept on B void. I'm keeping the second layer on void B. Now you can see that the second layer has been arranged now, and due to that second layer you can see that the void B has been covered up, because the second layer is placed exactly on it is placed by considering B as a center. That means the B is covered now. Now after keeping a second layer, you can see that now again we are getting two different types of void in the second layer also. In two different types of void, there is a one void which is already something is written in that void number 1. One void already something is written. While in second void you can see that it's a new void which has been formed. So something which is already written in the void in a void of a second layer is nothing but AAA. But the thing is that word A or the naming A was done in the first layer. That means I can say that the void A which was present in a first layer is now getting a common with the void present in a second layer also. So here I have the void A which is common between the first layer and the second layer. There is one new void has been formed. Now I'm calling that new void as a void C. Void C, that is a new void which has been formed here in a diagram or in an animation. You can see that the void C which is written now. So now in a second layer we have two different types of void, that is a void A which is common between the first and second layer, and the void C which is again a common between, which is new void which formed. The void B is covered, that means void B was the void which was present in a first layer, but now in a second layer the void B is not visible because the second layer balls are exactly placed on the void B. Okay, now after that, so here I can say that till now I got three different types of a void. The three different types of a void, which three different type I can say? Void A, void B and void C. Here I got three different types of void. Now let's see, each void is surrounded by how many sphere? Now I'm talking about the three-dimensional packing. So if you wanted to know that how many spheres are there around a void, then you have to consider two layers only. For a void you have to consider two layers. Now let's see how many voids are. This void B is surrounded by how many sphere? Void B, which was present in a first layer, but now it is covered by the balls of the second layer, is surrounded by how many sphere? As I said, you have to consider the void between the two layers, not more than two, and the number of spheres which is surrounding the void B is called as the coordination number of void B. And again I am saying you have to consider only two layers. So void B is surrounded by, you can see that from the lower layer, let us consider any one void B. So any one void B, you can see that from the lower layer, that is the first layer, the void is surrounded by the three sphere. It is three sphere, and from the upper layer it is surrounded by the one sphere. That means I can say void B is surrounded by 3 plus 1, that is 4 sphere. Void C, now let's talk about the C void. In void C, again you can see that void C is surrounded again by the 4 sphere like a B. Only the things are slightly opposite. In case of C, it is 1 sphere from the first layer and the 3 sphere from the second layer, but ultimately surrounded by 4 sphere. Then we have the void A. Void A, it is surrounded by how many sphere now? So I can say simply that void A is surrounded by, again, only void A surrounded by how many sphere? Then it is surrounded by 3 from the lower layer and the 3 from the upper layer. That means it is totally surrounded by 6 sphere. 6 sphere, that means I can say 3 plus 3. So those voids which are surrounded by 4 spheres are called as tetrahedral void. So these are called as tetrahedral void, that is a void B and void C is called tetrahedral void, and the void which is surrounded by 6 sphere, that is the void A, is called as octahedral void. What it is called? Octahedral void. So here ultimately during this packing I got two different types of a void, that is one is called as tetrahedral void and the other is called as octahedral void. So tetrahedral void which is surrounded by 4 spheres, and the octahedral void which is surrounded by 6 sphere. In a simple cubic packing, we had learned about the cubic void. This cubic void is present in three-dimensional AAA type packing. In three-dimensional AAA type packing, there was the void which was formed in AAA type. Those voids were surrounded by 8 sphere. 8 sphere means how? 8 sphere, 4 sphere from the one layer, 4 sphere from the second layer. So the void which is surrounded by 4 plus 4, that is 8 sphere, is called as cubic void. The one which is surrounded by 3 plus 3, that is 6 sphere, is called octahedral. The one which is surrounded by 4 sphere, that is 3 plus 1, is called as tetrahedral. This plus means I'm talking about the two layers. Everywhere you can consider that for knowing how many spheres are there around the cube, we are considering two layers. Okay, so till now I got two different types of void, tetrahedral and octahedral. The other thing that tetrahedral and octahedral doesn't represent the number of surrounding sphere. Instead, it represents the shapes. Tetrahedral voids are in a tetrahedral shape, and octahedral void, the shape of octahedral void is like a star. If you join the centers of the surrounding sphere, you will get a star. And octahedral void, three-dimensional structure of a star is considered as a octahedral void. So, or octahedral shape. So octahedral void is nothing but the one which is surrounded by 6 spheres. So till now in the diagram we had arranged the two different layers, that is the layer A and the layer B, and we got the two different types of void, that is a void, tetrahedral void and octahedral void. Now let's see how the spheres are arranged in case of tetrahedral and octahedral void. Tetrahedral void, as I said, it is surrounded by four spheres. Let I'm considering the void B. For the void B, you can see that there is a four sphere. How those four spheres are arranged? Three from the lower layer. One. This is second one. And there is a third one. So three from the lower layer. And there is a one sphere which is from the upper layer, that means this one. So this is one sphere from the upper layer, and this was the void B which was present in the first layer. In case of C, exactly opposite thing, the one is from the lower layer and the three from the upper layer, and this void which has been formed is called as a tetrahedral void, which is surrounded by four sphere. Now why it is called tetrahedral? Because when we join the centers of these four particles, we get a tetrahedral shape. Or I can say when we join the shape, the centers of these four particles from the center of void, you will get a tetrahedral structure, and that's why it is tetrahedral structure means something like this. Three from the lower layer, one from the upper layer. So this void is called as tetrahedral void. Now the next one, as I said, we have octahedral void. Octahedral void, which is surrounded by how many spheres? Then answer is 6. Now let's see how those 6 spheres are arranged in case of octahedral void. It is void A. I call void A as an octahedral void, and as I said, there is a total 6 spheres which are surrounding it. That is 3 from the lower layer and 3 from the upper layer. So octahedral void. Three from the lower layer and the 3 sphere from the upper layer. So here between these 6 spheres, the void which has been formed, I'm talking about this void, this region. So this void which has been formed, this void is called as octahedral void. Now we are calling it as now when you join the centers of these neighboring particle, suppose this 3 from the upper part, this 3 from the lower layer, what you will get? Upper layer like this and lower layer like this. That is a star shaped structure which appears like octahedral void. Or when we join the centers of these 3 upper layer particle and 3 lower layer particle with the center of the void, you get an octahedron structure, and that's what is called as octahedral void. Now in case of tetrahedral and octahedral, as I said, tetrahedral void is surrounded by 4 sphere and octahedral void is surrounded by 6 sphere. As the number of spheres, surrounding spheres goes on increasing, I can say the shape, the size of a void also increases. So from tetrahedral void and octahedral void, I can say that the tetrahedral voids are smaller in size, while the octahedral voids are bigger in size. So in case of second layer, we have got these two types of void. This is void in second layer. It is we have two types of tetrahedral. There are two voids which are tetrahedral B and C both. But in a second layer, the C void stand for tetrahedral and the A void stand for octahedral. Now I'm going to place the third layer on this second layer. Now the time to keep the third layer on this second layer. Now when the third layer is kept, when I'm keeping the third layer, therefore we are ultimately what we are doing, we are just keeping the layers on the voids instead of keeping it on the spheres on a spheres. Instead of that, we are keeping it in on a void. So in a second layer, first layer I said that whether you keep, in case of second layer, I said that you keep the spheres of second layer either on void A or void B of the first layer, because A and B both was same when there was only one layer. But now the second layer, there is a two different types of void, and both are having a different nature, the different name, different shape, etc. In second layer, we have the two voids, that is a void A and void C, and void A is tetrahedral. Void A is a octahedral, while the void C is a tetrahedral void. Now I'm keeping the third layer. First I'm keeping the third layer on tetrahedral void. That is now the time to keep the third layer on second void, on tetrahedral void, that is a void C. So now let's see in a diagram, we are keeping the third layer on tetrahedral void. So after keeping a third layer on tetrahedral void, you can see that again after what you think which type of layer it is, whether it is it matching with the any of these two, the first two, that is the first or second layer, then I can see that the third layer which has been kept, it is exactly like the first layer, because if I'm removing the balls of the second layer, you can see that the third layer balls will be exactly come on the balls of first layer. So here the first layer and the third layer which we kept on the tetrahedral void is having the same arrangement, and hence I can say that since they have a same arrangement, so it is called as AB type packing. Now it is a three-dimensional AB type packing. What is capital? The first layer arrangement is A. Second layer balls are not exactly above the first layer ball, so the second layer will be called as a B. First layer is A, second layer is B. The third layer which we kept is again A. Suppose if I am keeping the fourth layer now, then fourth layer will be, once you start keeping the third layer on tetrahedral void, then after that beyond all the layers will be kept on the tetrahedral void only. That means when you started with the tetrahedral void, you have to follow the same arrangement, because the crystallines, in a crystalline solid, the arrangement of the particle is same. If you start with the octahedral void, then throughout the solid the layers will be kept on the octahedral void. So here we are keeping on the third tetrahedral, so A, B, A. Again if you place the third tetrahedral void, the next layer, that is the fourth layer which you will get, will match with void B, and if it is matching with void B, that means layer B. So I got AB type of packing. Now let's see the same arrangement which we had done in this animation in a very short, with a very short form or small animation, that is here. Now in this case, the first layer which we were having, that is a hexagonal close pack layer. Here we are using a hexagonal close pack layer. Hexagonal close pack layer whose coordination number is 6, where each sphere is surrounded by the 6 atoms. On joining them, which we get a hexagonal ring. So here I am taking a small part of this diagram in this case. Now in this animation you can see that we are having the same hexagonal layer. That means the layer which is surrounded by the 6 spheres. Now these 6 spheres, now again just compare these two diagram. This is in a large or in a bulk I can say, and I'm just considering a small part of this diagram over here. Now if you consider in this any one layer from the first layer, you consider any one layer, any one sphere from the first layer, and you just count, you will get the 6 sphere over here, and those 6 spheres will form a 6 voids, and there is a void's name. If you observe, then you will come to know that AB, that means they are alternately AB is there. Similarly here also in this animation we are also, I'm just writing the same way, that is AB. So we have two types of void in a first layer, that is A void and B void. Now we kept the second void. The second void is second layer. The second layer was placed on the void B. So I'm doing the same thing here. Here also I'm keeping the second layer on the void B. When we kept the second layer on void B, you can see that here we got a new void, the void C, and surrounding to the second layer you can see that there is a void A also. Since I'm not extending the diagram to a throughout, that's why the void A is not surrounded by, but the second layer here in the diagram you can see that second layer is, we have only 3 spheres of the second layer. On those 6 or 7 balls, only 3 balls comes. So void C. Now void C, we kept the third layer. Where the third layer is kept, the third layer was placed again a tetrahedral void, which is a, what was the tetrahedral void? The void C was tetrahedral. So now here also I will keep the third layer on the tetrahedral void. Now when the third layer is kept on a tetrahedral void, the question arises that how many spheres will be there if you are keeping the third layer, then how many spheres will come on that 3 sphere? Then answer is that total 6 spheres will come on that particular 3 sphere. Now the void C is, there is a single void, but what I said, we are observing a small area. It's like I'm in a solid, I'm just looking for this much area. So in this much area there is a 6 spheres, above which there is a 3 sphere, but again in the same area, since again after A B will come, after B again the A will come. We are considering a small part of the full arrangement. We are considering a small part, that's why we cannot see the other spheres. But you are going to, when you will see the same arrangement in a bulk, you will come to know that there is a 6, above 6 there will be a 3, above 3 there is a, again 6 will come. Again 6, again 3 will come, again 6, again 3. It goes on, that means you get AB type packing. So from A layer 6 sphere, from B above that 6 you will get only 3. From the B layer above that 3, again A will repeat. So again you will get a 6 sphere, again above 6 you will get a B layer, that is again 3. So if I'm asking a coordination number in the case of this particular packing, what will be the coordination number of a sphere? The coordination number of a sphere. In this, I can say that coordination number of a sphere is going to be a 12. How the coordination number is 12? Here we are talking about the three-dimensional ABAB type packing. It's a three-dimensional ABAB type packing, three-dimensional. So I said here I want the coordination number. The coordination number is 6. How the coordination number is 6? You consider the first layer, that A layer. There is a one sphere at the center and the 6 are surrounding to it. So I can say that in a diagram, A layer is surrounded by the 6 spheres. A layer is surrounded by the 6 spheres from the same layer. Okay. Above A, who comes? Above A, B will come. The B, that sphere which is present at the center of the first layer, is surrounded by the 6 sphere of the same layer. 3 layer above, that is a B will be there. Above, after A, the B will come, and above A again the B will be there. So A 6, B it will be 3, and again B will be 3. That means total is how much? Then I can say total number of spheres which are touching to a single sphere is 12. So in case of ABAB type packing, the coordination number is 12. So here we got 12 as a coordination number. Okay. So 12 is a coordination number. Now in the case of 12 is a coordination number for the ABAB type packing. This ABAB type packing, in the three-dimensional ABAB type packing, is also known as a hexagonal closed packing. Again, we are calling it as a hexagonal closed packing. Why we call it as a hexagonal closed packing? Let's see. See, when we join the centers of the particle from the first layer, when we join the centers of the sphere from the first layer, in this animation you can see that on joining the centers we are getting a hexagon. Okay. Then first layer, and again then third layer I am considering. When I am joining the centers of the third layer, again I get a hexagon, and in between these two A layer there is a B, that is a 3 spheres are there which is present between these two A spheres. That means they make a triangular shape. So in this diagram or in this animation you can see that here on joining the centers of the particle from the 3 different layers, the lower layer A, 6, B, a triangle which we get, and again a 6 will come. So we are getting a hexagon. Again above this 3, again above it 6, again 3, and above 6. So we get a particularly, we get a hexagon, and that's why it is called as hexagonal closed packing. So here it is, this is about the ABAB type of packing. Now let's talk about the ABC type of packing. Now to get the ABAB type packing, we keep the second layer on tetrahedral void. Now let's keep this, we keep the third layer on tetrahedral void, so that I got ABAB type packing. Now it's a time to keep the third layer on octahedral void. Octahedral void, that means on which void? And again we have only 2 layers in this diagram. So now I'm keeping the third layer on octahedral void. Octahedral void, that is void A. So if I'm keeping it on void A, what will happen? So void A, you can see that if I'm keeping it on void A, we are getting a different layer. That layer, the balls of that third layer does not, it's not present on A, the first layer as well as on the second layer. They are forming some new layers. Some new layer is formed which does not matches with the either first layer or the second layer. That's why I'm giving it as some other name. That is, I'm calling this layer as a C layer. So now finally we got A, B and C layer. Now in C layer also, that is in third layer also, you will get 2 different types of void. That is a tetrahedral void and octahedral void. Now if I'm keeping the fourth layer on octahedral void, you can see that, as I said, if once you start keeping the layers on octahedral void, then you have to follow the same thing throughout the solid. So once I keep the third layer on octahedral void, then fourth, fifth, sixth, seventh, all the layers are going to be placed on octahedral void. So as I said, the third layer we got some new layer. Now when I'm keeping the fourth layer on again octahedral void, you may observe that the fourth layer sphere is exactly matching with the fourth layer, the first layer of the spheres of the first layer. That means A, B, C, then fourth layer is again A, and that's why it is called as ABC type packing. So now we got ABC type packing. ABC, ABC type packing. Again, sir, I'm talking about three-dimensional ABC type packing. Now, this ABC type packing, again, I'm considering as a small part in this, this animation. Here we are having the first layer, that is A type layer, on which we are having the second layer, that is we kept the second layer on void B. So when we kept the second layer on void B, we are having the two different types of void, that is a new void which has been formed C, and surrounding there is a void which act as a octahedral void. In actual diagram we know that it is octahedral void. Now we are keeping the third layer, on these octahedral void, that is on void A. So if I'm keeping the third layer on void A, you can see that again on that first 6 layers, how many spheres will be kept? The 3 layers, first there is a 7 spheres, 1, 6 surrounding, above which 3 layers of B, and if I'm keeping the third layer on A, how many again will form? 3 layers will form, 3 spheres will come, that means A, B, C. Again, the C void, you can see that is a void which is formed at the center, that void is acting as an octahedral void, and if you are keeping the fourth layer on octahedral void, you can see that the sphere which we are getting on the center will exactly matches with the first layer sphere which was present at the center. So here I can say that the octahedral void, if you are keeping the fourth layer, so if you are keeping the spheres on spheres on the octahedral void, you will get ABC type packing. That means A6, B3, C3, above which, that is a fourth layer, is again A. Again A, again B will come, again C will come. So now what will be the coordination number in this case? So for coordination number, I can say that if A is there, A, above A, B will come, above B, C will come, and below A again C will be there. A, 6 spheres, above which B have the 6 spheres from A, 3 surrounding sphere from B, and 3 surrounding sphere from C. So again the coordination number is going to be 12. So I can say that for ABC type packing also the coordination number is 12 only, like AB type packing. Only the thing is here, the A6, these 3 are from the B layer, and this lower layer 3 is from the C layer, while in this case A was surrounded by the BB layer from upper as well as from the lower side. So the coordination number of AB type packing and ABC type packing is same. Now when we join the centers of this ABC sphere, ABC packing, on joining the centers we get a simple face centered cubic packing. That means we get a face-centered unit cell. When we join the centers of these the particles of the ABC type packing, we get FCC cell. FCC cell, that is a face-centered cubic cell whose coordinate. So here I can simply say that face-centered cubic cell, the coordination number is 12, where the particles are present on the corner as well as the particles are present as the center of each faces. So here we got the two different types of packing, that is A type packing and AB type packing. Sorry, the two different types of packing, that is AB type packing and ABC type packing. In ABC and AA type packing both, here I can say AB type packing, which is also known as hexagonal closed packing. It's a three-dimensional hexagonal closed packing. That is also known as HCP packing. This is known as face-centered cubic packing, that is FCC packing, or also known as cubic closed packing, that is CCP. The coordination number of sphere in both is 12, here also and here also the coordination number is 12. Here the third layer is placed on tetrahedral void, while in this case the third layer is placed on octahedral void. So if the third layer is placed on tetrahedral void, you will get AB type packing. When the third layer is placed on octahedral void, you will get ABC type packing. In case of both, the packing efficiency is same. Packing efficiency, that is a space occupied by the atom. We will see it in a detail also. We will calculate that how we calculate the packing efficiency we will see. So in the case of this, In the case of both, the packing efficiency is same, coordination number same, packing efficiency is also same. For both, packing efficiency is 74%. The 74% packing efficiency means out of total available space, the 74% space is occupied by the atoms and the remaining space are vacant. The vacant space, that means they are in the form of void. So we did the close packed structure in a solid. Now in a close packed structure in a solid, there is a very important note that as I said, in case of AB type packing and ABC type packing, we are getting two voids, that is a tetrahedral void and octahedral void. So there is a relationship between the number of sphere, the number of tetrahedral void and number of octahedral void. Suppose in the packing, if there is a n number of spheres are involved, how many spheres are there which are forming a packing? I said n number of sphere. Then I can say that the number of tetrahedral void and the number of octahedral void, we have a relation between them. Number of tetrahedral void is going to be a 2n and number of octahedral void is going to be n. That means if I can say that if there is a suppose 1 lakhs of spheres are involved in a packing, then the number of tetrahedral void formed by those 1 lakhs of sphere is going to be 2 lakh and the number of octahedral void formed by these spheres is going to be a 1 lakh. So here the number of tetrahedral void, the number of octahedral void and number of spheres, between them we have this relation n to n and n, and this relation is very important for us. So just keep in mind this relation between the tetrahedral, octahedral and spheres. Now we just did the packing in a solid, that is how the spheres are arranged so that we get the 3-dimensional AA type packing, 3-dimensional AB type packing and 3-dimensional ABC type packing. Now in case of AB type packing and ABC type packing, we just saw that we are getting two different types of a void, that is called as a tetrahedral void and octahedral void. Now I just wanted to know that the position of a tetrahedral void and octahedral void in any unit cell. For us, for this chapter, for me, it's a FCC packing, that is ABC type packing is more important than AB type packing. Means to know the more and more, here in this chapter we are going to know more and more about the FCC packing, because face-centered cubic cell, throughout the chapter we are talking about only cubic crystal system. So I just wanted to know that if it is a face-centered cubic cell, that is which is formed in a ABC type packing, if there is a tetrahedral void and octahedral void, then what is the position of tetrahedral void and octahedral void in a cubic cell, where they are present? Tetrahedral void, as we know that these are the voids which are surrounded by the 4 sphere, and octahedral void which are surrounded by the 6 spheres. So let's start with the tetrahedral void, where the tetrahedral void is present in a FCC cell. So suppose if simply I'm just taking a FCC cell, unit cell having the 6 sides, having 12 sides, 8 corners, 6 faces. Now I'm dividing this unit cell into 2 parts by drawing in vertically like this. So we are getting a 2 part. Then I'm dividing it horizontally also, that is in this plane, and then I'm dividing it in this plane. So ultimately I can say that here I had divided the 3 different planes are drawn in between to divide the whole cubic cell into 8 different parts. So here we are getting the whole cubic cell has been divided into 8 different parts. It's a face-centered cubic cell where the particles are present on a corner as well as at the center of each faces. So we have this FCC cell which has been divided into 8 small cubes. You can see the full cube is a 1 unit cell which has been divided into 8 small cubes. Now just think about the center of those small cubes. Those centers of a small cube is going to be a tetrahedral void. So that center of a small cube is a tetrahedral void. That tetrahedral void is present at the center of each small cubes which are present in that whole unit cell. So ultimately there is a 8 centers, 8 small units, 8 small cubes which has been formed after dividing the whole cubic cell. So I can say, as I said, each center have a tetrahedral void. So how many tetrahedral void is going to be ensured in the whole unit cell? So I can say in whole unit cell there are 8 cubes, each cube is having a 1 center. So there will be total 8 tetrahedral voids.